Welcome back, students. In this video, we're going to look at chair flips and talk about that chair conformation a little bit more thoroughly. The first thing that I want to start with is looking at how to draw chairs. When you see a chair conformation drawn in a textbook, you don't really recognize how difficult it is to have you draw a chair conformation that looks good. It takes boatloads of practice. Now, if you have a good textbook, like I use David Klein's Organic Chemistry, that one really does a nice job of walking you through the steps of drawing chairs. And his process and my process are a little bit different, so I want to show you mine. The first thing I want to show you is your chair conformations. Notice how I said conformations as in plural. Here is one chair conformation on the left, and this is another chair conformation on the right. And these are two different chairs, and we want to be able to draw both of them. What is happening at room temperature is one chair is flipping to the other, and we're going to get to that in a moment. First, let's focus on how the heck we're supposed to draw those. What I suggest you do is you draw two lines that are parallel to one another, and you want them to be slightly offset. If I'm starting with the chair on the left and I'm trying to mimic that, let's just notice really quick that this line and this line are parallel to one another, but they're not starting and stopping at the same place vertically. So I'm going to draw an offset pair of lines. Then what I do, once I draw that offset pair of lines, which I'll repeat over here, is I finish this process with some triangles. Notice how if I go back up to the chair that's already drawn, I drew a green dot on one carbon. I'm going to draw a green dot on the other carbon. If my parallel lines are facing this way, carbon is going to be somewhere down here, and that means that I need a longer line pointing down, and then I come back and connect. My other carbon is going to be somewhere up here, so I need this line pointing up, and then I connect. I don't really like that. I'm going to change that angle a little bit. That's better. It's going to take a boatload of practice to get the hang of drawing chairs. So before you even go into practicing drawing chair flips, just draw some chairs. Because what also happens is students will get used to drawing, say, the chair on the left and then not be able to draw the chair on the right. So we drew the chair that was on the left that I boxed in yellow. Now if we want to draw the chair on the right, what we need to do is draw a set of parallel lines, but instead of those parallel lines pointing downward and to the right, what will happen if we want to mimic this chair is we're going to draw our set of parallel lines pointing upward to the right. So there's a slight difference there, and you want to make sure that you can draw both chairs. The next thing I want to do is show you a model of a chair conformation. So here is my model of the chair conformation. And notice how I have these two bonds highlighted in pink. These are my parallel bonds. And then the atoms that I had put dots on in green, that one is here covered in Play-Doh, and that one's here covered in Play-Doh. So this is one of my chairs. What's happening in real life is this chair has enough energy for this atom to come down and this one to come up. And if you see, what happened was the directionality of my parallel bonds ended up changing. We're going to spend more time on chair flips in a couple of moments, but I just wanted to draw your attention again to parallel lines, one green atom, another green atom. Notice how I have axials down here, like we talked about in our last video, axials pointing up here, and then our equatorial positions around the equator. Let's move into an example where you're going to draw a chair. I have a set of chairs outlined below, and I just want you to take a moment and practice drawing them. You will need the practice, and don't be upset if your chair looks ugly the first time. It's probably going to, and it's okay, because it just takes a lot of time to get the hang of making good-looking chairs. All right, if you want me to walk you through it, I'd be happy to. What we're looking for is drawing a set of parallel lines. So I'm going to draw these parallel lines that I just highlighted. So I draw my set of parallel lines and they're offset and they're pointing slightly down and to the right. Then what I do is I connect down and connect up. My other chair is going to have a set of parallel lines. Oops, wrong one. Here and here. Those parallel lines are now pointing slightly up and to the right. And so that means that this carbon is down and this carbon is up. Now let's move on to actually flipping a chair. Chair flips are going to be one of the most difficult things that you probably do in organic chemistry because it requires a lot of spatial visualization. If you have a model kit, then this will certainly help you. The problem is that the models that you're used to seeing in general chemistry, the ones with the balls and the flexible bonds, those are horrible for chair flips. They're very difficult to get them to flip. So if you have models that are similar-ish to these, then that would work nicer. Now here's the problem. These models, this particular set of models, is literally the best chair flipping models I've ever encountered. And I can find them no places on the internet. You can find ones that are similar-ish, but not this size, not this good. And this was a hand-me-down. So if anybody finds these on the internet, will you please post them in the comments so that I can buy more? I want to buy all of them. They're really good. So here we are, we've got our chair. The key that I want to talk about first is when we flip a chair, the most common misconception is students think we're flipping this like a pancake, right? They're like, oh, here I am flipping like a pancake. And no, there's not a rotation that's going on in here. We're not taking the molecule and rotating the molecule. We're seeing that the bonds within the molecule are twisting and changing their position. So if we go back to what's happening here, we have our two highlighted bonds in pink that are our parallel bonds. And we have our atoms that are in turquoise. And what happens is you pull one of them down and you pull the other one up. So on paper, what you're doing is this atom here is coming up and this atom here is getting pulled down. And when that happens, where you used to have a set of parallel lines pointing slightly down and to the right, the parallel lines end up shifting so that they're pointing up and to the right. And I just want to show that again, where I pull down and look, now I'm in boat where these two are parallel to one another. And then I pull up and you see that shift happen here. In addition to recognizing that we're not pancake flipping and instead we are pulling one carbon up and one carbon down, another thing that we need to be aware of is during the course of the chair flip, all of your axial positions turn into equatorials and all of your equatorial bonds turn into axials. If I bring your attention to the bottom figure, I want to show you how this hydrogen that I just highlighted in yellow says axial up. When this hydrogen that's highlighted in yellow goes through the chair flip, it will now be at the equatorial position. And it will be still pointing slightly up. So the directionality of the bond doesn't change. If you had an axial that was up, pointing above the plane of the ring, then even after you do the chair flip, you're still going to have a bond that's pointing above the plane of the ring. So you'll have axial that's in the upward position, which will switch to equatorial still in the upward position. Whereas if we look at equatorial right here, that's pointing slightly downward. When this flips into our new chair conformation, it will change to axial, but that axial position will still be pointing downward. So it's important to recognize that the ups and the downs don't change because if we look back at our ring again, notice how on our ring there's axials that are pointing straight up, right? There's axials that are pointing straight down. There's equatorials that are pointing slightly up. There's equatorials that are pointing slightly down. So above the plane of the ring and below to the plane of the ring, that part's not changing. It's just the equatorial and the axial part that ends up changing. I know that that's really hard to see, so I wanted to make sure that we had a moment to make the picture really big and see those things again. All right, now I want you to see this at full picture. Let's look again and say that we have our pink bond and we have our pink bond and they're parallel to one another. Notice how they're parallel and pointing in this downward direction. What's going to happen is we're going to pull this carbon that's slightly up in comparison to the other one. We're going to pull the upward one down, and this carbon that's slightly down in comparison to this one, we're going to pull that one up. When we do that, the direction of these bonds is going to change. So we'll end up going through the boat conformation. So if I pull just this one, notice how now these are parallel to each other and also parallel to the ground. So this 1, 2 bonds are in parallel to one another, and this is our boat conformation. Down here, you're seeing the flagpole interactions that we talked about earlier. Then we take this one and we pull it up, and notice how now our bonds are still parallel, but they're pointing slightly upward, whereas originally they were pointing slightly downward. So let's look one more time at something different. I have a small piece of white Play-Doh on this position, and I want to show you how the axials become equatorials. So this is an equatorial position right now. This is an equatorial position that's pointing slightly above and up and away from the equator. If I pull this one up and then pull this one down, notice how my equatorial position became axial, but it's still pointing upward. Because it was pointing upward to begin with, it's still going to point upward at the end. It's just now that position is not around the equator. Instead, it's pointing straight up. Now what I want to do is add a substituent to our cyclohexane. Once you're comfortable drawing your cyclohexane rings as chairs, then you're going to graduate to mono and disubstituted cyclohexane rings. Let's go ahead and first start by drawing a cyclohexane chair, and then we'll add a methyl to it. Remember that when I'm drawing chairs, what I'm doing is drawing a set of parallel lines, pointing one direction or the other. I like to point slightly down first. If you prefer to point them up first, that's fine. And then finishing that off, right? This is in equilibrium with my other chair, where what I'm doing for my other chair is now I'm going to draw my parallel lines pointing slightly up and to the right, and then this is down, and then that is up. When we're looking at drawing monosubstituted cyclohexanes, like this one asks you to draw methyl cyclohexane, I think students do the best if they choose to put the substituent either where I highlighted in yellow or where I highlighted in blue. So pick one. The other thing that I think students do best with is drawing your first position, your first substituent as axial, because it's easier to see the axial positions than it is to see the equatorial positions. For example, if I draw my axial position on the blue carbon, I would point this straight down. Remember that if there's nothing on the end of the line that I just drew, then it's assumed to be a methyl. So this is indeed methyl cyclohexane. Now, remember that what we did was we took this carbon and we pulled that carbon up, and we took this one and we pulled it down. When we pull that carbon down, this is the part that's going to blow your mind that you probably need models for. When you pull that highlighted in yellow carbon down, that carbon is now pointing downward on the page, and you know where it shows up in the drawing is here. And I know that most of you think that it's here, and it's not. No, because what you did was you took the one that was in yellow and you pulled it downward. Remember how you started with your parallel lines, right? This carbon and this carbon and this carbon and this carbon were your parallel lines. And then you switched the directionality of your parallel lines. These are your parallel lines. What you're changing is the direction of the carbons I've highlighted in yellow and blue, pulling one down, pushing one up. And so now you see where it can get really confusing. and students end up thinking like the ring has twisted slightly, and it's not. We're not twisting anything, right? What we're doing is we're pulling one carbon down, we're pushing one carbon up, and during that process, the directionality of the bonds changes. So that's one key to success in your chair conformations, is recognizing that if, say, this is carbon 1 right here, and this is 2, and this is 3, and this is 4, then over here, this is 1, this is 2, this is 3, and this is 4. Now let's go ahead and finish drawing our second ring where I have the methyl drawn in on the first carbon. And now that methyl, I drew it as axial pointing downward, right? So this was axial pointing down. That means when I flip it, I need my carbon, my methyl, to be equatorial because axials turn into equatorials, but it still needs to be pointing slightly down. And it is really hard to draw equatorial positions. You're going to need lots of practice so that you can draw something that looks like it's actually equatorial. There's a section that I call no man's land, and no man's land is where students will draw a bond, but there's nobody knows, is that supposed to be axial? Is that supposed to be equatorial? So you want to make sure that you're looking at a good reference text to get the hang of where those equatorial positions are going to be drawn. Sometimes it's easier to draw all of the positions on, but if you do that, so if you're like, oh gosh, it's so hard, how am I gonna draw the equatorial position for, number 1 here? I'm gonna have to draw this one and draw this one. Well, yeah, but you know what? If you don't put a hydrogen on that one, you actually are saying that there's a CH3 there. So you have to be really careful with chair conformations because some of the tricks that students use to help themselves end up communicating incorrect things on tests. So this one looks kind of equatorial down to me. I like it. Now, what if you were to put on your methyl at the 4th position? So let's just do that really quick, and we'll go ahead and say this one's equatorial and down. So I just want to redraw this. And now let's put our methyl here. So here I put it axial up just because I think it's easiest to start there. So we put the axial up on carbon number 4. We go through the process. Remember that this carbon is this carbon. And so now if we had axial up to start with, we would need to draw, ooh, that's kind of iffy. I don't like that. Equatorial still up. That's axial down. So like that. See, even sometimes I don't like the angles. I don't love that angle. So what I'm going to do is I'm going to keep the axial there as reference and put a hydrogen in. That way, I think it's easier to see that the equatorial is actually equatorial. So we've drawn 2 different ways to illustrate the chair flips for methyl cyclohexane. Can you start on the other carbons? Absolutely. Is it easiest to do it this way? Yeah. You should just pick carbon 1 or carbon 4 and start with that. Let's talk some more about that equatorial position and why it's so special. We drew some methyl cyclohexane on the earlier page. And if I look at the chair conformation here for methyl cyclohexane, notice how I have that methyl group that has a pretty big electron cloud because it's got a whole bunch of atoms. And then there is a hydrogen here and a hydrogen here. These electron clouds are getting too close to one another. And this is a type of steric strain. This steric strain actually has a very specific name. This is called 1,3 diaxial interactions. Let's talk about where that name comes from. Notice how your CH3 is axial and it's at the first carbon. And then here's carbon 2, here's carbon 3 where you have that hydrogen. At the third position, you have an axial hydrogen that's interacting with that CH3. And if you were to count the other way, you would have a second hydrogen, also 2 carbons away from CH3. And that's where you get the di, right? So we have at the first and third position, we have, no matter which way you count, whether you're coming toward me or away from me, you have 2 axial interactions that are leading to steric strain. And because of this additional strain, this makes your axial position, when you have a substituent in the axial position, that's less stable. So this steric strain makes for a less stable conformation. So what does that mean? It means if axial is not stable, then equatorial is. Because for equatorial position, you don't have 1,3 diaxial interactions. That CH3 is off into the equator. It's not interacting with those hydrogens. So equatorial positions are going to be more favored and more stable over axial positions. What I want you to do is give this a try where you draw both chair conformations of bromocyclohexane. And you know that when you're done with them, I'm going to ask you to tell me which one is more stable and which one's less stable. So give yourself a couple of minutes and then we can check back. All right, let's compare. So I went through and I drew my conformations for cyclohexane, making sure that I went through the chair flip. And now I want to add my bromine to it. Like I said earlier, I think it's easiest if you pick either the kind of up or down carbon and start by putting your extra substituent on one of those. So whichever one you pick is perfectly fine. Let's go ahead and we'll pick this one, right? And put your bromine here. If we call this carbon number 1, when we pull this carbon down, where I'm pointing my arrow, that is carbon number 1 now. So maybe that's one way that you can remember where that carbon is going to be, is you draw the arrow and where the arrow is pointing on your next chair, that is your same carbon. Now, if this bromine was axial and up, then when we do the chair flip, this needs to be equatorial but still up. So let's sneak in that equatorial position. I still sometimes like to add that axial just to give me some perspective before I draw the equatorial, because the equatorial is so hard to draw. All right, that looks pretty good. Again, I'm going to keep in that hydrogen for perspective purposes, just because I think it makes it look more clear that you are considering bromine being equatorial. And you know I wanted to ask you which one's going to be more stable. So which one is more stable, when bromine is in the axial position or when bromine's in the equatorial position? And hopefully you remember that we just said that when bromine is equatorial, that's going to be more stable because you don't have those 1,3 diaxial interactions. So this is going to be more stable of the two. And remember that both of these are existing at room temperature. They're in equilibrium with each other. They're the same compound with the same connectivity, with the same direction of atoms in space. And that's what conformations are. And so all that's happening is one carbon's going up, one carbon's going down, and they're flipping between each other in these two chairs. So this one is more stable because this one is less stable due to those 1,3 diaxial interactions that we talked about. Let's wrap up. In this video, we looked at drawing chairs, where we talked about drawing chair flips. Sometimes people call them ring flips. We discussed how axial groups change to equatorial and equatorial groups change to axial, but the direction, like above the ring or below the ring, that part doesn't change. We flipped a chair for monosubstituted rings and we assessed which one is more stable. In our next video, we're going to look at disubstituted rings. So stick around.